In this demonstration, you will learn how to use a standard Simcenter 3D workflow to prepare and analyze a structural model using a linear static solution. We're starting out with a crank arm part. It rotates about the left side, and then there'll be a force on the right-hand side. We'll go ahead and set up the model. You can see the application that we're in up in the banner. Right now we're in modeling. We want to go to pre-post. We choose the application tab and then click pre-post. It'll take us over to pre-post, and you can see all we have in the simulation navigator is a part file. There's a tab in the graphics window for the corresponding part. So it'll create a FEM and simulation file. You can see the file names that will be generated. We have our part file. It's essentially the same, except it will append fem1.fem and sim1.sim onto each one of those as it creates the new ones. For solver environment, we have Simcenter Nastran as a solver, structural analysis type, and then we click OK. We'll go ahead and create the solution. We see the solution name. Once again, the solver and analysis type. But now we have the solution type. We will do a standard solution 101 linear static solve. We create the solution, the dialog box expands, and you can see all the options that are here. There's some vertical tabs on the left that have more options. Right now we're just going to accept the defaults and create the solution. You can see in the simulation navigator the FEM file is the active part. So we have the part file, the FEM file, and a simulation file, with the FEM file again being the active model that's open. If we go in the simulation navigator and expand the FEM file, underneath it we see the idealized part and the master part. The idealized part is a referenced copy of the master part, and if we make changes to the idealized part, it will not affect the master part. We can also see the various parts that are open in the simulation file view. We just click the banner of this group. We have the simulation file, FEM file, idealized part, and part. And they're also available up in the banner. Under Window, you can see each one of the files and the parts that are open here. The way that we're going to move between them is we'll just click the various tabs in the graphics window. We're going to start by creating a mesh on the part. That's done in the FEM file. That's the work and displayed part right now. Go ahead and click 3D tetrahedral to go ahead and create a solid mesh. We'll take the default element type, C-tetra10. For element size, we're going to click automatic element size. You can see it generated 1.5, but what we need to do before that is to select the part, click automatic element size, and it will generate an element size value based on the geometry that you already selected. The mesh collector stores all the information about the mesh. We can take the default and it will create one for us, or here we're going to go ahead and create a new mesh collector. We're going to give it a name of steel. We need a solid property for this, so we're going to click Create Physical, and the main thing we want here is a material type. We want steel. And that's now selected in our mesh collector. Then we'll go ahead and generate the mesh. Now you can see the 3D tetrahedral mesh has been generated on the part. In order to add loads and constraints, we need to change to the simulation file. We'll just click its tab, and now the simulation file is the displayed end work part. First thing we're going to do here is go ahead and generate a fixed constraint. We want it on the inside of this hole. If we select one of the surfaces, that's all we're going to get. But what we want to do is change the method to tangent faces. And then when we select one, it will go ahead and select them all because they're tangent to one another. Click OK. It tells us it's created the local boundary condition group. And we can see the symbols that represent the fixed constraint on that hole. Next, we're going to add a pin constraint to this inside cylindrical hole. Go under Constraint, Pin Constraint, select that cylindrical surface, and it will infer the rotational direction, which is along this axis. Click OK, and now we can see our pin constraint. You can also see these being added to the simulation navigator. So we have the fixed constraint and the pin constraint. When we hover over each one, it will highlight it in the graphics window. Our last setup piece is a bearing load. We go under Load, Bearing, and we want to apply this load to the cylindrical surface on the opposite end of the part. So we'll select that surface. We're going to specify the vector. We want it in the downward direction, which is X. Come over here, choose X. We're going to add the force of 500 newtons over an angle of 180 degrees. Click OK. And now we can see that the load has also been created in the simulation navigator. For our solution, we've taken the default name. We can go ahead and rename that. We're going to rename it Structural Solution. And then press Enter. Now you can see the name has been updated in the simulation navigator. We can go back to our solution options, edit the solution, want the case control tab, and we're going to edit the output requests. So we'll just check on a few things here. We'll start with displacement. I'm going to make sure that that's enabled. We're going to go to stress, make sure that that one's enabled. And the last one we want to check is strain, and make sure that one is enabled. By limiting the number of output requests that you have, you will reduce the solution time. We right-click the solution and choose Solve. Once it's done, we are not going to review the results, and we'll go ahead and close the information window and the analysis job monitor. So we can go into post-processing and look at the results. There's two ways to get there. We can either double-click the solution here, which is what we're going to do, or we could have come over to the post-processing navigator, right-click the solution, and choose Load. We expand the solution, look under Displacement Nodal. We're going to double-click Magnitude, and we can see the results from that solution. The fixed end obviously has no displacement, and the displacement is going to be on the free end where the load was applied. We'll go to Stress Element Nodal, look at von Mises, and you can see the type of result that you have by looking up into the legend right here. You can see Stress Element Nodal, because when we change to our last thing that we're going to display, Strain Element Nodal, it's going to be hard to tell that anything changed based on the colors in the contour display. The values in the color bar have changed, but the display looks almost the same. But you can see up here it is Strain Element Nodal. This ends our demonstration on analyzing a structural model using the standard workflow in Simcenter 3D.